and thank you for joining us for the inaugural talk for the 2014-15 SIG webinar series. This year's series features topics in software infrastructure and development that enables our science. Webinars will focus on bridging communities, laying foundations for robust and useful software that address active areas of geodynamic research and HPC for big data. Today's webinar is being recorded and will be available for on-demand viewing through geodynamics.org. During the webinar, only the host and presenter will have their microphones enabled, so use the chat window to type in your questions or to communicate with others. Presentations in the series will be approximately 15 minutes in length, with questions and answers following during the remaining time. To kick us off today, we have Professor Anna Kelbert. Professor Kelbert received her Ph.D. at Cardiff University and is currently an assistant professor at Oregon State University. Her interest in inverse theory led her to the development of inverse methods to image global and regional electrical conductivity in the Earth's mantle, providing additional constraint on mantle melt and water content. Anna is a 2014-2015 EarthScope Distinguished Speaker, so look for her on the road this year. Today, Anna does not delve into her work in magnetotellurics, but in cyberinfrastructure, in her efforts through NSF'S EarthCube program to improve knowledge integration and accessibility within and across disciplines in the geosciences. In her talk, Earth System Bridge, NSF'S EarthCube Entry Point for Solid Earth Geosciences. So Anna, the screen is all yours.
Hi, thank you, Lorraine. There's some background noise. Yeah, okay, that's good. Can you hear me? I hope. Yeah, okay. Hi everyone. It's my great pleasure and honor to give this talk now. It's actually a very rewarding and interesting project that I am involved in, and I hope that you can get some overview, some idea about what we're doing here, and maybe get involved after this talk. At least that's my aspiration. So I'll be talking about the big picture first, which is the cyber infrastructure in general. Why do we need it? How much of a cyber infrastructure do we actually need, and why? And then I'll talk about the EarthCube, the initiative as such, the history, the governance, how to get involved, give an overview of all the existing projects, just so that you have an idea how this fits into the bigger picture. And then we'll talk about numerical models specifically and our Earth System Bridge project. What does it actually bridge? And then we'll get to some finer details, but we'll see how it goes. It's a very involved talk. I'm trying to cover a lot of ground. I do hope that you'll have a chance to ask questions later. Yeah, the arrow. So cyber infrastructure is an overloaded term. It can mean a lot of things. Data, anything from a simple data georeference database for geosciences to something much more involved. First thing is to see what kinds of what do we want to get out of the cyber infrastructure, and how do we want it to function. And of course, there are fears that have been expressed about cyber infrastructure and actually infrastructure in general. So in this case, the biggest fears that I've heard before are that the computer scientists are not sufficiently knowledgeable about geosciences to really make this useful for us, and they make it too complicated. That it should be flexible enough to allow original research, and that the training should be an integral part of this. User feedback and support should be part of whatever is being brought together. And the scientists should be in charge of how it functions, which is all very true. Now, assuming that we succeed, the vision of success is actually very reassuring, because cyber infrastructure will focus on eliminating the bottlenecks that we are currently facing, and it will eliminate the need for the pain that we're experiencing in doing all those chores that we have to be doing to maintain our data and our software in a usable state and shape. It will provide intuitive fingertip access to all kinds of facilities and data, and possibly even provide new understanding and research opportunities. So with that in mind, how much of an infrastructure do we need? And I think that this cartoon summarizes it very nicely. The character here is asking you to pass the salt, and then he says, I said, the answer is, I know, I'm developing a system to pass you arbitrary condiments. And he says, it's been 20 minutes, and the answer is, it's been, I'll save time in the long run. And of course, we don't want that to happen, but on the other hand, to really see the extent of the cyber infrastructure, I suggest that we can examine the problems that we would like to solve repeatedly and efficiently and robustly. So I would personally identify 4 of such problematic issues that we're all facing and that are our current bottlenecks. Problem number one that you could see here is scientific reproducibility, including benchmarking. And that is something that is a huge bottleneck right now in the geosciences. We face it when a student who's been working on a specific problem leaves, and we need to redo part of the work that has been done, or we have new data sets and we want to redo the old processing on the new data sets, or when we want to look at something that the colleague has done and verify it in our own way. You know, all kinds of issues. Actually, even repeating something that we did a few years ago could be a problem, as we have all experienced. And the reason is we actually need to record scientific workflows. Scientific workflow is the full information that you would need to reproduce the results, starting from the raw data. And that defines all of the conversion tools, all the processing tools. Any subset of that procedure is also a workflow. And poor workflow recording is really a problem. It introduces lots of grievances into our lives that we may not necessarily even notice because they are so inherent to our way of doing things. So that needs to be changed. But of course, the workflows need to be very flexible in many ways to really be useful. So first of all, they need to be modular, so that a scientist should be able to create a workflow chart and populate it with codes and procedures and metadata that describes each of the components. They need to be intuitive and should take very little time to create, because we don't want to do more chores than we have to. And they should be citable, so that we could track changes and bug fixes and propagate any information to the users of our workflows. And that making them citable would also provide an incentive for sharing, which is important. Incentives for sharing. They should be reusable, so that they could be saved remotely and easy to pull on later and pull out later. And we would want to share those workflows with members of our research group at first, and then possibly when our work is published, we would want to share them more widely for independent verification. They have to be non-prescriptive, so that there should be no restrictions on the languages that we use for our tools, the operating system that this is going to ultimately run on, formats. Those prescriptions should come from standards, but they should not come from the system itself. And then finally, they should be flexible. I don't know if you can see this at the bottom, but they should be trivial to clone. It should be trivial to clone somebody else's workflow or your own workflow and populate it with in-development components. So that would also enable benchmarking. So the solution to this problem, as I see it, is that we need to record our workflows, and they need to be available for critical review, replay, and creative modification. And The peer-reviewed manuscripts are, of course, the tip of the iceberg, and they should be placed in the new context with the data that supports them and modeling that supports. Of course, that would also enable benchmarking, because you could populate an existing workflow with your own in-development components where necessary, and immediately have benchmarking capabilities. Now, the obvious question that you might all have in mind is, well, I'm already spending a lot of time complying to the data management plan, and this will take this should require much more than I'm already doing. Well, hopefully that's not how it's going to work, but we'll get to that. Now, the problem number 2, a key bottleneck that we all have, is interdisciplinary communication. It's so difficult to share digital information between disciplines that we all struggle with it greatly. This is due to all kinds of issues, especially the language barrier and formats. So the reason this is such a big deal right now is we are actually starting to address really complex problems, more Earth system type problems, and we do want to connect pieces together to really understand those complicated processes that we're working with. So the solution would be, as I see it, sharing workflows and coupling codes across disciplines, and that needs to go across the language barrier. So there is some standard set of utilities that could be applied to help us with this. And the first one is standardized metadata, which, of course, by default, it aims to describe a resource for ourselves and our colleagues. That it uses very domain-specific terminology that nobody else outside the discipline would necessarily understand. And we would need controlled vocabularies to for cross-domain communication. Now, ontologies are a tool of artificial intelligence that allow you to describe the relationships between concepts and their hierarchy, and they use controlled vocabularies to do this. Semantic web is a set of tools that allows use these ontologies to parse human speech, human description of a concept, and to do it intelligently across domains. So my suggestion is a cyber infrastructure that would be useful for interdisciplinary communication would need to be internally supported by both metadata standards and semantic tools, semantically enabled as a term. Now, problem number 3 is model data integration, and that is a big issue, especially for us modelers. Data communities use their own standards, they use their own conventions. The observations, of course, are inexact and sparse, as opposed to modeling predictions, which are far from exact and continuous, but more so than the data. The data could and should be used for model validation and calibration, and that is very rarely done because of the complexity of merging these two worlds. On the other hand, models could and should be used to explain the data and test hypotheses to get a conceptual understanding of the processes that are behind the data that we obtain. And the solution would be to interpret them jointly on a 4D globe, which is a virtual globe that has a notion of 3D Earth and time. So the solution is actually quite involved. It's a complicated problem to solve, but the cyber solution would be to have the front-end API, which lets us access all those resources. We also need big data storage on distributed file systems because there is no feasible way to store all data that we might want to access across disciplines at one place. We need data access solutions using web services that are semantically enabled, like described previously. We need remote access to high-performance computing, preferably in the cloud, and we need, based on the selection of the user, those remote modeling capabilities and the web services should be evoked to merge the two worlds, the modeling domain and data domain. So, of course, all of that needs access to workflow tools so that we could reproduce this later. And now problem number 4 is, of course, the data and software management, which is compliance to the data management plan, which is a great step in the right direction, but we obviously need help to do those chores. You know, just like washing machines have been invented to wash our clothes. We need clean clothes. So we really need tools that would help us do this. It's an essential thing to be doing, but we have very few standards. We have very few very little help with metadata management right now, and the system that we're designing should be able to help us do those chores more efficiently, take away all those pain. We should not be spending our time that we could be spent doing science, stuff that computer scientists could do better, more robustly. If you imagine the whole system as I'm just inviting you to imagine how this could work, and this is my personal understanding. Let's start with the data. There is big data. It's a distributed file system, so we need access to that. We don't want access to just any data set. We want very pointed access to just the specific data that we are interested in, and we would do that through web services, which would be semantically enabled so that we could search across disciplines, and all of that could be connected to this front-end virtual globe. And now there is also the modeling world, the numerical models that need to have access to high-performance computing, and these could be connected to the front-end virtual globe through interdisciplinary model coupling with some inherent multi-scale interoperability checks to connect things that should not be connected together. And that also requires semantics and cross-domain metadata. Then there is the backbone, which is the workflow management, because whatever we do in the system needs to be recorded and reused and shared. And for sharing, we want research groups, a notion of research groups, and that would really be the carrot. That would really make sense in the context of using the system. If the system is able to immediately provide us with advantages that we have not had otherwise, we would be very motivated to use it. And the biggest advantage we could think of is the ability to immediately share our exact, precise workflow, starting with the data sets, all our processing tools, all of the modeling capabilities that we're using with a specific versioning with our colleagues, so that a colleague could immediately comment, modify. And that is something that would be the ultimate carrot in using as far as I can. And then, of course, we could share more widely when we're done with a particular project. Now, this would also enable social network-based open peer review, because any component could be commented on, you could ask questions, and those questions would be answered in an open manner rather than by email, and those emails being lost and questions being asked repeatedly by multiple users, having to repeat the answers to them. Then there should be integrated pathways for community input, because after all, we want scientists in charge. if a scientist is not happy about something, they should be able, they should have a way to notify developers. And then the cherry on the cake of this whole system would be disciplinary data simulation. But we're obviously far away from making that possible. So the summary on my understanding of cyber infrastructure in general is that I see it as a comprehensive technical solutions to these key problem areas: scientific reproducibility, interdisciplinary communication, model data integration, and data and software management. The areas which are currently bottlenecks, and we need help with those. So the ultimate goal would be to allow a more systems-oriented and sustainable approach to the earth sciences. It should largely take the burden of data mining and maintenance off us, while streamlining knowledge accumulation. So now on, I just want to focus on EarthCube as such, and I'll give an overview of what that is, the vision, the governance, and how you could get involved. And we can move to my project. So the EarthCube vision, and this is a standard NSF slide that they're showing, is to link all those components together into something that's interoperable. So transform the conduct of data-enabled geoscience-related research, create effective community-driven cyber infrastructure, allow global data discovery and knowledge management, and achieve interoperability, which is should ring a bell, because it's very similar to what I've been talking about just now about cyber infrastructure. They're obviously thinking along the same lines, which is good. Now, the EarthCube Journey is another slide that the EarthCube test governance is showing. It started in 2011 with some dear colleague letters, and there was a charrette with some brainstorming sessions about the community getting together, mostly the computer science-oriented people, getting together to answer some questions like, do we need cyber infrastructure in geosciences? What kind of problems do we want to solve? What are the goals to achieve? And that resulted in white papers and expressions of interest in 2012. And in 2012, there was a roadmaps and concept design initiative. And then there were a range of end-user workshops. There have been 27, I believe. Stakeholder alignment survey, we'll get to that. And the first round of solicitations, that was in 2012. We're currently in the second year of these funded projects. And I'll get to the actual funded projects in a second. There was a 14.5 million budget in 2013 if projects were funded, and we're now in the second year of the first round, and the next solicitation is coming up in March, I believe. This was it. Okay, so the stakeholder alignment survey, which was a separate Inspire funded project. PI was the Jewel Gershenfeld. It might still be ongoing, and this is a summary of what they found. They had quite a few respondents from different subdisciplines, and this table here shows how much they communicate, and this is the percentage of those reporting daily, weekly, or monthly communications. And of course, they discipline to within the same discipline, people do communicate, which is reassuring. People much more rarely communicate across disciplines, and in some cases they don't communicate at all, or close to none. Like for instance, geophysicists and geographers don't tend to communicate. And then there are computer scientists, data managers, and software engineers, which all communicated between themselves, but not so much with the main scientists. So that could be improved. And the end user workshops, actually 29 end user workshops, and I think 2 are still upcoming. And of these, this community, the CIG community, have been most involved with the community modeling workshop. There's been also the EarthCube workshop, physics, rock deformation, mineral, and the marine geophysics workshop is still upcoming in December. And the point of those end-user workshops was to collect information about the specific problems, specific bottlenecks that the communities are facing that they would like to solve with cyber infrastructure. The current projects involve test enterprise, include test enterprise governance, which is a project to organize the real governance together, help organize, facilitate. I think the Inspire project here is stakeholder alignment. I'm sorry that you can see this very well. Some resolution. The conceptual designs, there are actually 3 funded projects now, and the third one has not been announced yet, are conceptual ideas of how the architecture could work and the full EarthCube architecture could work. And the research coordination networks are designed as something reasonably small, and I think the original idea was up to 300,000. And the idea is to get people talking within the communities, rather across the communities that don't typically talk. And then the final group of awards were building blocks. No, I'm sorry. This has some. Okay. Okay. The building blocks projects. And those are current, and some more building blocks projects have just been funded. There is one by Team Aachen, led by Team Aachen, to do the web services component. There are other projects relevant to data management. I probably shouldn't focus on all of them right now because it's because of the time constraints, but I will focus on specifically this one, the Earth System Bridge, which is my own project, rather the project that I am involved with, and that relates to this community. Now, the organizational timeline. This is the timeline to organize the governance together. Another slides that governance is showing. They do the assembly workshops first, crowdsource governance concepts, and provide a recommendation to the NSF. This has now been done, and we now have a demo governance framework. And here too, which is starting right now, is to establish organizational structure, safe convergence, and EarthCube architecture. We are not in the next phase yet, so we don't know what it's going to be, because the idea is that the initiative will be there are various roles that you could play in EarthCube, and I'll go through them briefly. There is the Leadership Council. There are 3 standing committees: Science Standing Committee, Technology and Architecture Standing Committee, and the Council of Data Facilities. And then there are engagement and liaison teams, and then there are working groups and special interest groups that any EarthCube member could. And the Leadership Council is tasked with the scope and vision for EarthCube. It doesn't exist yet. Well, neither the scope, vision, nor the council. Actually, the council is being put together as we speak. There are 2 members who've just been voted for. Yolanda Gill is a representative from the technology community, technology standing committee, and Basil Gomez is from the science standing committee. And then there will be 5 Council. The Science Standing Committee is tasked with making sure that the science use cases are what governs development, and also engagement of scientific community, help on data management plan, the strategy on data management plan. Then the architecture and testbed are the task of the Technology Standing Committee. There is the Council of Data Facilities, which is probably efficiently functioning right now. They self-organized and starting to share services now, I believe. And then there are teams to liaison national and international consortia collaborations, and the engagement team that to go out to the community at large. This is a very busy figure, but it shows overall governance organization of EarthCube. So the Leadership Council, everyone will report to the Leadership Council. It will be the EarthCube community, which could at any time initiate special interest groups. There are also working groups that could be initiated by anyone, either the EarthCube community itself or the teams or the Leadership Council. The working groups are intended to be a little bit more formal. They will get some funding up to $10,000 for meetings. No salary support for working groups. No salary support for anyone here, actually, for that matter, except for the funded projects. The Science Standing Committee and the Technology and the Council of Data Facilities all report to the Leadership Council. There is also the Engagement and Liaison Team and the Office, which supports the whole system. Then there are science and technical funded teams which will be in close communication with the committees. If you're interested in more information, this is all recorded, I believe, so all of those links will be saved. Please go ahead and check it out. Recorded webinar about the committees and teams. You could propose a working group or volunteer for any of the committees. The committees are all open. You could jump in board at any time and make your voice heard. Specific suggestions. The implementation plan for the governance, this is how they describe it. Sprint number 1 with lots of obstacles, and then there is sprint number 2 with hopefully less obstacles. And we are right now somewhere here, September to December, working meetings, and we're still in the process of, they are still in the process of forming the governance structure. And developing the architecture framework is a matter of 1 year, less than a year. To start having some test beds. Okay. Now on to the numerical models. Remember, we were just looking at this overall scheme of how all of the cyber infrastructure could work. Now the numerical model part is essentially here. So I'm removing everything that's not directly relevant, all relevant, but we'll be focusing on so the models, high performance computing, and linking of the models together into the disciplinary model coupling and the metadata resources. Semantic resources. So out of the building blocks, these are particularly relevant. They're all relevant, but this is a closer collaboration. Even our project and this I'll get back to this project in a second. But, the software stewardship is the project to describe workflows and store them robustly. It's possible to share them. Synergy is a project. Synergy is a project to describe those resources semantically. Then integrating discrete and continuous data hopefully help for with model and data integration. And I should note that there are currently no funded projects to link all of this with high performance computing, cloud computing, big data transfer, storage solutions like Hadoop, MapReduce, and all of those are actually gaps that could be filled. Now, the Earth System Bridge is one of the building block projects. It's been funded at the level of close to $2 million for 2 years, and it's a very large collaboration. We are currently in the second year. This includes NCAR, NOAA, hydrological community. So Coaxi is the water community, or obviously, and NCAR then the climate and weather communities. And the deep earth processes I answer to in my Now, the project is focused on interoperability between models, models and data, and modeling frameworks at all levels. There's been a lot of feedback from the communities and a lot from the individual modelers, and we're seeking more feedback. So, the specific user needs that we are trying to address, seeking to address, are quite wide-ranging, and this is a slide from my collaborator Scott Peckham. He is very precise in putting this words, which is anything and everything that makes it easy. That's precisely what we're after. We want to connect existing models as possible, and for that we develop metadata standards and standard model interfaces and middleware, such as Rigrid, and provide make it easier to prepare input data for models and provide access to HPC. So what do we bridge? We bridged primarily 3 modeling. And ESMF is the weather, climate, coastal space weather. And of course, we all climate very developed. So we could learn from that. CSDMS is the surface process model, and I'll talk about that in a second. And CIG. My role in this is to help create the numerical model metadata. So the metadata and the controlled vocabulary for numerical models is my task in this project. Communities that we're trying to learn from. CSDMS community has it's our counterpart in the surface dynamics community. It hosts numerical models, it maintains standard documentation, provides remote high-performance computing facilities, holds workshops. One of the things that it does host a range of models from different disciplines. One of the things that it also does is provide a remote interface for model coupling and remote HPC facilities. That's something that I don't think CIG currently has. So you could configure a model. This is just one specific model child. You could configure components that are coupled to child, and each of these have the input configuration parameters. Data could be uploaded to the server, and then you click a button and run everything on the HPC facility. So, of course, they're solving very multidisciplinary problems, quite complex systems, and let's look at how they manage this. There is quite a bit of infrastructure behind it. So, first of all, they have working groups and focus research groups. It's a large community of over 1,000 members as of today. they have multiple ways to make models talk to each other. So how can two models differ? There could be differences in the programming language, in the computational grid, time-stepping differences, the variable names, and the variable units. And all of these require intermediate solutions. So I'll briefly stop on and describe some of these, and particularly the semantic mediation, the standard name, that describe the input and output variables of the models in a unified manner. The first thing is to reconcile differences with standards, and of course, if we don't have a central hub, it quickly becomes unmanageable. So they're using a central hub for everything, and they use some powerful tools. They use Babel for language interoperability, and then Voca, Caffeine, the regreaders, including multi-processor spatial regreader of ESF. I'll get back to it. And they developed their own interface standards, the basic modeling interface, and the further interface through Boca to couple models. So the basic modeling interface is something we'll stop and discuss briefly. So those are the tools that are used by CSDMS. So it's not a standalone application. It's a the reason it's so powerful is because it's employing as many tools as that in a coherent manner. This is a little bit involved, but the basic idea is that the BMI is this. It's designed to be a non-invasive part of your numerical model. It has to be a module in actually a few subroutines in your numerical model that you need to write, but they're non-invasive and relatively simple. And once you have those few numerical those few descriptions, this interface within your code, it's called BMI enabled, and at that point it can be coupled with any other components within CS. And the framework is such that the BMI is simple and non-invasive. Then there is something called the CMI on top of it, and that interlinks with the service component framework. But the BMI is quite manageable. It's that little input that the numerical modeler needs to provide to make the components compatible. The standard names is the controlled vocabulary that has been developed within CSDMS. It's a result of quite a few years of effort. And the BMI uses standard names so that the models can talk intelligently and exchange variables, such that one model's output variable is another model's input variable. And you could go online and check it out. There are process names, quantity names, assumption names, and such like. The basic rule is that it's a long name. So when you implement the BMI, that links your internal the internal code to those long names. It's not something that's invasive. You don't have to change your code anywhere. You just specify which of the long names, the CSDMS standard names, correspond to your internal variable name, and that makes it BMI compatible. And the rule is there is an object part, the operation part, which is optional, and then the quantity name, and perhaps the most relevant example here, earth material, second invariant of deviatoric stress, where the deviatoric stress tensor is the quantity, second invariant is of is the operation name, and the whole thing applies to the earth material object. There are also process names, attribute names, assumption names. The part that's currently missing is the standards for the model coupling metadata, because the reason it has not been complete yet is because it's actually quite an involved task. There should be a way to structure the information about the models rather than just list it. The variables should have a purpose. They could be output configuration. Each of those variables could have assumptions associated with the variable, grids associated with the variable. And then there are overall modeling assumptions that we would want to use to describe the code. The physical processes that are being modeled, the assumptions on those physical processes. Those are all part of the description. The time scale, spatial scale. So to make it manageable, we would need to provide questionnaire tools to easily create this information. And once the information is in the system, it would also be machine readable, and it would assist modelers in preparation of the model for coupling with the BMI or other ways of coupling. So we intend to leverage that, or rather we are leveraging it from the climate community experience. And something that they have and has been employing for many years now is the common information model. That's a schema. It describes numerical model components. It also describes simulations and grids and data. That is actually represented as an UML diagram and then transformed into an XML schema, and that is supplemented with domain-specific schemas to describe a component. These are used to validate XML documents, and there are questionnaires that could be filled in, and there are tools to search and compare and visualize the responses. The reason they need this to operate is, of course, the fact that they are inherently interdisciplinary. They model the ocean and the land and the rivers and the lakes and the clouds and the atmosphere, and there is no way around it. Of course, what's missing here in this picture is the solid Earth component. That's what we like to fill in. The CIM schema is used by ESMF, which is a large model coupling framework for climate modeling. It's also used by NS, the European counterpart of that framework. The tools that exist to work with the schema and the related documents maintained by the ESDoc group, and our collaborators at NOAA and NCAR are involved with that. Now, unfortunately, those tools are not complete yet. Since the theme was created as part of through an iterative process, it actually needs to be generalized and updated in various places, and we are involved in doing that. And also the questionnaire is a work in progress, but that's also good, because that is a cutting-edge technology that we can help shape and provide our input at this stage, which is a critical stage of shaping reshaping the theme and the CIM schema, and also shaping the questionnaire. The reason we choose to use CSDMS standard names rather than something that the climate community has been typically using is because it's more relevant and more complete. The CSDMS standard names description is more coherent, and there are crosswalks between the two, that are being developed. So the choice is CSDMS standard names for controlled vocabulary, and these will, of course, be extended to our community. And we want to adapt the CIM schema and the tools for the actual numerical model. So my tasks in this project are to extend the controlled vocabulary to our domains relevant to CIG, and also to help define the numerical modeling method. There is also another part which is which NSF'S is working on, and that is enabling the coupling between PIA and CSDMS frameworks and providing a specific example. I won't dwell on that for now because that's a great topic. It's very involved. So the final deliverable looks something like this. The user would fill in a questionnaire about the model, and the questionnaire results would be stored in this model coupling metadata format developing. And then the user could use those climate community tools and to view and compare the results, the metadata inserted, and the CSDMS tools could be used more easily because once the metadata is in the system, the basic modeling interface, the BMI, could be semi-automatically created. And then all BMI-equipped models could also be coupled with models wrapped for other modeling frameworks, and there is also a component that describes modeling frameworks themselves. So framework interoperability is the overall overarching aspect. And I'll end 13 minutes late, I'm so sorry, with this advertisement for the workshop we're going to hold April 30th to May 1st. That's a 2-day workshop that will help us provide with help us in defining the accurate CSDMS standard names for the CIG community, and also give us direct feedback. Should be mutually useful both for developers and love you to get involved. Thank you.
Thank you, Anna, for giving us this webinar today, and thank you everybody for hanging in there with us as we solved our technical issues. If you have questions for Anna, go ahead and type them into the chat window, or you can raise your hand. There should be a tool on your top of your browser, and I can enable your microphone. So we'll wait a few minutes to see what questions there may be. I'd like to let you know that our next webinar will be on November the 13th, and it will feature Dr. Jed Brown from A&L, who will talk to us about best practices in software development in his talk, Software Design and Packaging for Extensibility, Provenance, and Sharing. I don't see any hands. I don't see any typing. Then maybe we'll wrap it up because we're running a bit over time. Thank you again, everybody, for spending the extra few minutes with us. And thank you, Anna, for introducing us to this initiative. We look forward to interacting over the next several years as these concepts and tools take shape.
Thank you, Lorraine, and everyone. Appreciate your patience. I'll accept questions offline.